we have compared reactivity of carboxylic acid derivatives in nucleophilic acyl substitution reactions by looking at the electrophilicity of carbon of the carbonyl group and also by looking at the leaving group ability. So we've been able to determine that acid chlorides, for example, are the most reactive carboxylic acid derivative in nucleophilic acyl substitution reactions because of the two reasons. So these are the most reactive carboxylic acid derivatives. Amides are the least reactive, and the reactivity scale is going this way. So acid chlorides are more reactive than acid anhydrides, which are more reactive in turn than esters, which in turn are more reactive than amides. So acid chlorides are the most reactive, followed by acid anhydrides, followed by esters, and then finally amides. Now, a consequence of this reactivity scale is that it is possible to make a less reactive carboxylic acid derivative from a more reactive carboxylic acid derivative. For example, it is possible to make an acid anhydride from an acid chloride. It is also possible to make esters from acid anhydrides. It is possible to make amides from esters. So a less reactive carboxylic acid derivative is possible to be made from a more reactive carboxylic acid derivative. Not only it is possible to make carboxylic acid anhydrides from acid chlorides, it is also possible to make esters from acid chlorides and also amides. Yeah, so we can go therefore in conversions from acid chlorides to amides, from acid chlorides to acid anhydrides, from acid chlorides to esters, from acid chlorides to amides. And also acid anhydrides can be converted into esters and also to amides. That's possible. Esters can only be converted into amides when you reach the least reactive carboxylic acid derivative in this scale. Then that's it. It's not possible to make a more reactive carboxylic acid derivative from it. Also, it is not possible, for example, to make an acid anhydride from ester. So why is that so? Well, let's write the scheme in general for the nucleophilic acyl substitution reaction. So something like that. So this is a carboxylic acid derivative in general. This is a nucleophile, and this is the nucleophilic acyl substitution reaction product with the leaving group. Now, for this reaction to be likely, obviously the nucleophile or this unit must be a better nucleophile than L. So that's very important. So this should be a good or a better actually nucleophile in comparison. Now L should be a better leaving group than the nucleophile itself. So L should be a better leaving group than Nu. Otherwise, the reaction will not take place. For example, we can make an acid anhydride from an acid chloride by reacting the acid chloride with the carboxylate ion. So you can imagine the carboxylate ion here, and of course L is Cl, and then we get an acid anhydride as a result of the nucleophilic acyl substitution reaction, obviously plus Cl minus as a leaving group. So the carboxylate can come, of course, attack carbon, carbonyl group leaves, it's reformed, and then Cl leaves. Now, the carboxylate should be a better nucleophile than the chloride, otherwise the reaction will not take place. The chloride ion should be a better leaving group than the carboxylate, otherwise the reaction will not take place, and the chloride ion is indeed a better leaving group than the carboxylate ion, that is, as we have seen before. So that's exactly why it is possible to make a less reactive carboxylic acid derivative from a more reactive one, but not vice versa.